Today, uh, before we get started today, I'm going to pass it over to Terry, who's got a couple of announcements.
Yeah, two quick announcements. We are recruiting people to come to the Meta-Analysis Training Institute, or as we affectionately call it, MATI. Those applications are due at the end of the month, and we will put that link in the chat. And then the other thing that we're looking for is I have, with a colleague here at Georgia State, Jonte Myers, we have gotten a postdoc from NSF. And the postdoc is aimed at STEM researchers who want to learn about meta-analysis and systematic review. It's a 2-year postdoc where they'll work with us and learn how to be meta-analysts and look at STEM issues. So if you know of anyone, I'll put that link in the chat too. Thanks.
Cool. All right. So to our main event, I'm really pleased to welcome Zhipeng Hu. Zhipeng has a doctorate from the statistics department at Northwestern University. His work looks at the intersection of machine learning methods, natural language processing, AI, and the systematic review processes. And so today he's going to be presenting one of his dissertation papers, I believe, that I just really appreciate it because it's so it's on the topic of screening for systematic reviews, and this is a space where there's been a lot of innovation. A lot of people are throwing machine learning tools out there, like left and right, but Zhipeng's work brings really principled statistical perspective to answer one of the big questions about this process. So I just appreciate he's representing stats in an era when we seem like we're overwhelmed by machine learning. So I'll pass it over to him. We'll use our usual rules. Please feel free to type questions into the chat during the presentation, and we'll collate those, interrupt if it seems like it's really important. Otherwise, we'll have plenty of time at the end for discussion. So thank you again for coming.
Hi, everyone. Yeah, my name is Zhipeng, and I really appreciate this opportunity to talk about this dissertation paper of mine. And I really appreciate your interest in this topic too. Let me share my screen and show the slides. Okay. So today's topic is going to be on this so-called automated literature screening process, and it's going to be, so the first section of this presentation would be about what is automated literature screening, and the second part would be about this algorithm we proposed in our paper, and the last part would be questions and discussions. And I would be paused for comments and questions. But if you have any questions, as James mentioned, please feel free to just interrupt me and ask. This algorithm that I'm gonna introduce is not a complicated algorithm, but it might be difficult to understand. So my goal is to have everyone understand what is automated literature screening and why this algorithm works by the end of this talk. So yeah, what is automated literature screening? I believe that all of you have already know what is literature screening in a systematic review. In one sentence is basically we have find thousands of candidate papers by searching some bibliographic databases, right? And we have to manually screen those paper records one by one to identify a small group, like 100 or 50 of relevant papers. And what is automated literature screening, automated literature screening, is basically instead of we human beings screen all of those candidate papers, we have some kind of predictive model to predict the probability of relevancy for each candidate paper. And we only screen the papers with a higher probability of relevance. And in this way, we saved some of the screening workload, and we hope we are able to identify most of relevant papers in the candidate pool, if not all of them. So the model can be anything. When I was working on this, there weren't ChatGPT, and most of the models are machine learning models like support vector machine, like random forest, and things like that. And there are some like larger natural language, large language models used. But right now we have much more advanced models like ChatGPT and some other like Gemini developed by Google, things like that. Like this model can be any model, and all we need is that it need to be able to predict the probability of a candidate paper, of the probability of being relevant of a candidate paper. So let me show you an example workflow of automated literature screening. I don't think this is a good name, but in the literature, most of the authors would use this name, automated literature screening. So for example, it can work like this. The first step is initial screening. We human reviewers would randomly screen like 4,000 candidate papers. So assume we have 10,000 candidate papers identified, and the first step would be we randomly screen 4,000 of them. And the next step is we use the 4,000 screened papers to train a model, to train any model, like a random forest model, as I mentioned. And this model, we call it M. So now we have this predictive model M. We can use this M to sort the rest 6,000 papers based on their predicted relevancy. And we only need to screen the papers that are predicted to be most likely to be relevant. So this is one example, and like in the machine learning world, it's called supervised learning, because we have screened the papers as a training set, and we train a model based on it. So is there any comments on this process or any questions?
I have a question.
Yes.
So you used a supervised machine learning technique in this initial stage, which is automated literature screening. Does it mean that you have human generated label? So you compared human generated label versus machine generated label?
At this, so we do have human generated labels. That's the first 4,000 papers. Basically, this process, you're exactly right. We are trying to generate some labels for those papers. The labels are basically relevant or irrelevant, yes or no, right? Those labels. And we are using those labels as training data. If we can think about it as a logistic regression, we basically train a logistic regression based on the human labeled data. And this logistic regression model would be able to predict kind of the odds or like the probability of a new paper being relevant. This is like a very simple like toy example, so we do not have to compare anything. We just use the model's labels as it is.
Thank you so much.
Yeah.
Keisha had another question. to clarify, when you say that humans would screen the documents with high probability, what would be high? Like,
Right, this is a great question, and this is why I proposed this algorithm. So yeah, I'll save this question. Like, you will be able to learn more about this later. This is great.
and then one more just quick clarification. When you say screening, are you talking about the title abstract screening process or like full text?
Right. That's another great question. Like, the reason we have this two-step process is, like, first we do title abstract screening, then we do full text screening. Is the first thing is, like, full text screening takes a long time, and also it's hard. It's harder to get the PDFs of all of, like, for example, if there are 10,000 papers, it's a huge work to download 10,000 PDF files for the papers. But I mean, this is basically the reason why we are having this two-step process to reduce the workload. But nowadays, I feel as the technology developing so rapidly, in the future, all of the papers, like the full text of all of the papers, can be easier downloaded and organized for training. So I would assume that in the future, it's probably going to be more full text screening. Like, we only do it once. Like, but right now, because of some technology issues, we are doing this two-step. So what I am talking about here, you can think it as title and abstract screening. No full text here yet. Okay. And so I have another example. This is a little bit more complicated than the previous one. So it's basically machine learning, or like supervised learning with model updates. It's like, instead of only training one model and use that model to predict all of the rest papers, we first screen. In this case, the first step would be we first screen only 2,000 papers. And we use this 2,000 papers, or like labeled data, to train a logistic regression model or any other predictive model. We call it M1. And after this, we select 2,000 candidate papers from the unscreened candidate pool. And those 2,000 papers are the ones that has highest predicted relevancy based on model 1. So we update this model once here, and we use additional. So after we have this additional label data, we have 4,000 papers screened, and we use this 4,000 papers to train a new model. We may call it model M2, and we use M2 to guide how we are gonna train the remaining 6,000 papers. And we stop when there's time to stop. Is there any questions regarding this process? Okay, yeah, so you see, we can update model after we screened 2,000 candidate papers. So why don't we just update our model after we screen 1,000 papers, right? Like, we could update like model once, twice, 3 times, 4 times, right? So if we want to do this in a more extreme way, we would just randomly screening one candidate paper, and we train a model based on that one record, one label data. And when we select another data, another paper to screen, and use that screened paper to train the next model, M2. And we can do it many times. We have M2 and we screen another paper and we get M3. And we use M3 to predict the rest unscreened papers, and we select one that has the highest predicted relevancy. And after we screen that paper, we have a new model. So we keep updating those models. This is kind of the most commonly used and popular method people are using right now. I see there is one comment. Right. Yeah. So it's like, you see why this the reason why this active learning algorithm is the most popular is not because it makes the most sense. It's because it do not require us to make arbitrary decisions, right? So for example, how do we decide how many decisions how many papers we are going to screen before we update our models? Like some softwares would update every 10 decisions. Some software would update their model every like 50, 100, 200, who knows, right? But this way, at least we do not have to make that decision because we just update every time we have a new paper screened. And so this is basically how this automated screening work in real life and in most of those softwares. And I am prepared to show you an example very briefly. So here, so this software or like this platform is called Abstractor. And this one is I used for my dissertation paper. And you can see here, there's one task called demo. Here are some more information. I had about 5,000 papers, and I have already screened 6 of them. And in order to start screening, I'll just click screen. And this is a little bit slow right now. But what I want to say is there are so many tools out there right now. Another example is AS Review. This is one of the one that are I'd say more up to date. Like this is state of the art, but it's more updated one, and it's probably easier to use as well.
Abstractor's been really slow the last week. I know this from personal experience, so you might have a little bit of a tough time with it.
Okay, yeah, probably we just skip. But the idea is basically we screen, we tell the kind of the model. Yeah, here we have it. So I think I am able to select if this paper, it has title, it has abstract, and I'm able to select if it's relevant or irrelevant, or I'm not sure, right? So I just keep screening, and the model will be updated when there is new screened results come. And yep, and it's just like this, right? Is there any questions regarding the whole process? Like what is automated literature screening? And I'll go back to the slides. Do you see something in the chat? Yep. So the big question is what we just mentioned. The big question is basically how do we know when we can stop this process, right? We know we have a model, and that model will be able to give us a recommended order of all of those paper records, and it will suggest us screening the papers following this order. But how do we know when should we stop, right? In this example, the red papers are irrelevant papers, and the green papers are relevant. And if we stop here at the red line, we're going to get 75% recall. I mean, by the way, recall means the proportion of relevant papers being identified. Here, there are 8 relevant papers, and we are able to identify 6 of 8 relevant papers. So the recall is, 75%. And also, we are able to save about 62% of screening workload. The screening workload is basically measured by the number of records we didn't have to screen, the proportion of the proportion of all paper records that we didn't have to screen. And another way, right? If we stop here at this kind of brown line here, we still have 75 recall achieved, but we only saved about 45% of screening workload, right? And another choice is this black line. Here, if we stop here, we have already identified all of the 8 relevant papers, so we have 100% recall. We have found 100% of the relevant papers in this candidate pool, but we only saved about 17% workload. And if you think about it, it's basically a trade-off between these two measurements. One thing is what the proportion, the recall, the proportion of relevant papers identified. Another thing is how much workload we can save, right? For example, if we have 10,000 papers, a 17% of workload saved, it doesn't mean much, doesn't mean anything, right? We probably don't even want to use this. And what's more challenging in practice is that before we screening all of those papers, we do not know what the recall we have achieved. For example, if we stop here at the red line, because all of the rest papers are unscreened, we just don't know how many relevant papers are left missing. And also we of course, we don't know how many relevant papers are there in this candidate pool. So there isn't a very efficient way or like a reliable way for us to even measure this recall. For us to even know like when we stop, what proportion of papers are missing. And this is why it's so hard to answer this when to stop question. So I'll pause here. If you have any questions or comments regarding this process, please feel free to ask. Okay, yeah, so I think we have learned about this problem, this question. The next step would be for me to introduce this algorithm we proposed in our paper. It's a resampling-based algorithm. So here's how this resampling algorithm works. So the goal of this algorithm is to provide some guidance on when to stop. Okay, in order to use this algorithm, the first step is we would need to draw a random sample of k relevant papers from the candidate pool. In this case, we have the 3 random sample papers marked by a red circle. And we would want this sampling process to be sampling with replacement, which means the same relevant paper can be sampled multiple times. And in order to do this, this may sound easy, but if you think about it, in practice, we do not know which part of the papers are relevant and which ones are irrelevant. Here we know the ground truth, right? We know the red papers are irrelevant and the green papers are relevant, but in practice, how do we do this sampling?
Can I ask a clarifying question?
Yes.
Is this the set of papers that have been given a predicted probability after some set of human screening?
No, it has to be completely random. It's like, so here, the first step does not involve any machine learning algorithm, any ChatGPT stuff. Like, we do not have anything yet. We do not have model yet. We just draw a random sample. So in order to draw a random sample of relevant papers, it's actually all we need to do is we just draw a random sample of many papers, right? We keep randomly select one paper from the candidate pool and screen it to see if it's relevant or not, right? If it's relevant, then we have one random sample of this relevant paper, and we keep putting those samples back to the candidate pool, so it's sampling with replacement. Is there any question regarding how to achieve this random sample process?
Just curious, you said this study started from before the advent of ChatGPT. So now we have ChatGPT. Then how this process will be changed if we include ChatGPT?
Thanks for this is a great question. Yeah, it's so ChatGPT. The difference between ChatGPT and other machine learning models is that the interface is kind of different, right? Because other machine learning model, most of the previous machine learning models will give us like a probability or something like that, or like yes or no answer, right? But nowadays ChatGPT is more like a chatbot, like we have a conversation with ChatGPT. But I think the idea is kind of similar. It's basically we give ChatGPT a paper and let ChatGPT answer if this paper is relevant or not. I'm not sure if you have used GPT-4. GPT-4 allows so the free version is GPT 3.5. It's like we type in questions and get answers from ChatGPT, but GPT-4 would allow us to upload PDF files. So we're able to just upload a PDF file and ask GPT-4 if this paper is relevant or not. We get an answer. So one thing we can do is, we only screen papers that GPT-4 thinks is relevant. I admit there is some randomness in this process, but still, like GPT-4 would propose a recommended order. Like GPT-4 would suggest some of those papers to be screened first and others to be screened later. I hope that answered your question.
Yes, thank you so much.
Yep. Okay, so basically we have a sample of 3 papers. What we do is we put those 3 papers back, but we memorize which papers are our sample. And the next step is basically we have either GPT-4 or any machine learning model to help us rank those papers. And this order should be based on basically the predicted relevancy. Like more papers that are more likely to be relevant should be screened earlier than after. And after this, we just keep screening following this order, and we can stop screening. This is the answer to when to stop. When we stop screening, when all of the sampled papers are identified, And in this case, it's in this red line, right? After this green paper is screened and identified, we probably don't need to screen it once because we already screened it in the sampling process. But after this paper is like screened and identified, we stop screening. And we are able to prove that the probability, if we follow this process, if we use this resampling algorithm, the probability of we have recall greater than or equal to C can be like 90%, has to be greater than or equal to 1 minus C to the K. K, if you remember, is basically the number of relevant papers that are sampled at the beginning. On this graph is 3. But for example, when K equals 10, basically if we have randomly sampled 10 papers with replacement at the beginning, and we follow this process stop at here, the recall, the proportion of relevant papers identified greater than or equal to 80% would be greater than or equal to almost 90%. So this algorithm gives us an answer to when to stop and also when we stop, like how good the performance would be. And I will pause here to see if there are any questions regarding this algorithm. And after this slide, this page of slide, I'll start explaining why this works.
Can I restate what I think you're saying at the bottom and see if I got it right?
Yeah.
So if you've done, in this example, your initial round starts with K with 10 sampled papers with replacement from your total set of papers. And then based on that initial resampling, you've trained a model that gives you a set of probabilities, right? And you keep screening until the last, then you rank order all the papers based on the probability of being relevant, and you keep screening until the last paper has a probability of being relevant of 80%, which means that your probability of having gotten all of your papers is just a little under 90%. Is that what you've just described?
Right. Yeah.
Okay.
So the probability of we have identified more than 80% of all of relevant papers is about 90%. And it's greater than 90%.
Mm-hmm. Okay.
Just another clarification. Maybe I misunderstood this when I first read your paper. Are you using the sample that you screened with the random sample with replacement that you screened to identify this initial set of K papers? Do you get to use those labels to train the algorithm or not?
No.
Oh, I see.
No, we are not allowed to use this information. So the papers are put back to the candidate pool, right? But we would not let the machine learning algorithm know if those papers are relevant or not. Of course, we are human screeners. We know if they are relevant or not, and we are using this information to stop. But this information is unknown to the machine learning models. So this is why it protects this process, because machine learning models, any machine learning or like ChatGPT, like they do not know if those papers are relevant or not. They do see those papers, like they see those papers just like any other candidate papers, but they just don't know. They shouldn't use that information to train themselves.
I see. Okay. Thank you.
Thanks. Yeah, that's a great question. Yeah, I know that's kind of very hard to. It's kind of confusing part. So it's kind of why. So we are trying to build this information barrier to use as kind of an independent audit of the performance of the machine learning model. If the machine learning model knows this information, right, you can tell, like you can imagine, like it will classify the 3 sample papers to the top of the of this chain, right? Because it's already known those 3 papers are relevant, so those papers are likely to be screened at the beginning of this process, and the whole system falls apart because it doesn't guarantee anything. Right.
Yeah, I have a follow-up question. Does it mean that you did not train the model using human labeled data?
We can, so after we have sampled this K relevant papers, we can do whatever we want. So basically, we get the information of the 3 relevant the 3 sample papers, and after that we can use anything like to train a model, like just like what I showed before, like example 1, example 2, example 3. We can, yeah, like we definitely will be using human labeled papers to train the model. But I mean, so if you think about this this order of papers, it may not all depends on the likelihood of being relevant, because at the beginning we probably do not even have a model, right? So at the beginning it's probably just still random sample, random order. We randomly screen like 10 papers, and after that, I'm here. So for example, from the first paper to here, we just randomly select a paper to screen. And after that, we have a model, and all of the following papers are proposed by the model, like the abstractor platform, if you remember.
Yeah, that makes sense. So the models is keep updated. So yeah, that makes sense. Thank you so much.
Right. Yeah. You can think, yeah, we just keep updating the model, and the model will propose a new paper, just like what we did in the abstractor platform. And yeah, why would this algorithm work? So let's have a deeper dive into the algorithm. So assume, in this example, assume we have 5,000 candidate papers. That's basically after we searched on Google on those kind of bibliographic databases, we have 5,000 paper records. We have 5,000 papers, and assume that there are 100 relevant papers in this candidate pool. And here, the green ones are irrelevant, and the blue ones are, or like the darker ones are relevant papers, right? So any automated screening process would give us a rank like this. It will rank all of the papers from 1 to 5,000, and it will suggest us to screen from 1 to 2 to 3 to 5,000. And this process also implicitly implies a relative rank for all of the relevant papers. So in this slide, if we only focus on the relevant papers, you can see the 100 relevant papers are also ranked by this algorithm, whatever by this machine learning model, whatever the model is, whatever the update, model update and the model training process is, it basically ranks the 100 relevant papers. And so we only look at the 100 relevant papers and their relative ranks. It's like here, I just removed all of the irrelevant papers to help us think this process. And we could draw a random sample of 10 with replacement, of course. We could draw a random sample of 10. And in this case, the random sample papers are marked with red. This is one way to draw a random sample, right? And we could also draw another random sample. This is another way to draw a random sample of 10 with replacement. Those purple papers are randomly selected. Right? Assume, but if the sampling result were like this, if the sampling result were like this, the 10 red papers are selected, and we follow the resample algorithm, we would be stopping at this point. We would be stopping after all of the relevant papers are identified, right? So if we draw a random sample like this, we would have identified 100% of the relevant papers, 100 out of 100. Because we stop here, because we stop when all of the relevant papers are screened and identified. And however, if the sample is different, if we do it again, like we draw different random sample, in this case, we would be stopping here, right after paper 90, relevant paper 91. And if we stop here, we would have identified 91% of the relevant papers, so we have a recall that's equal 91%. And so in order to have a recall that's greater than 90%, right? In this case, we have 100 relevant papers, and in order to stop after this red dotted line, in order to stop after this red dotted line, we must have at least one relevant paper being sampled. That's not just the bottom 10 papers, right? We have to have one sampled paper here on the right side of this red line. And so the opposite of that scenario is we have all random papers selected on the left side of this red line. So in that case, we have a recall that's less than or equal to 90%. And the probability of that happening is basically we do a random sample. We do random sampling 10 times with replacement, and all of those random samples are coming from the left side of this red line, and the probability of that happening is 90% to the 10th power. I know this part is kind of tricky, but so I know this part is tricky, so I will explain it again, right? So in order to have recall less than or equal to 90%, we will have all of the relevant paper samples drawn from the left side of this red line. And the probability of that happening once is basically 90%, because it's basically we have a random sample of any of those 90 papers out of 100, right? If we draw a random sample once, the probability is 90%. And if we do it again, right, and we do it with replacement, so the whole space doesn't change at all, right? The whole probability space doesn't change at all. So if we do it again, and that happens again, that probability is 90% again, right? And if we do it 10 times, that probability is 90% to the 10th power. So in that case, the probability of we have recall that's less than or equal to 90% is 0.9 to the 10th power. And it's the opposite case. The opposite scenario is the probability of we have recall greater than 90%, which is basically 1 minus what we just calculated, 90% to the 10th power. And this is basically how this works. If there are any questions, I'll pause here. I only have one more page left, but yeah, I think we have enough time to answer questions.
I think I'm going to ask a question here. So at first you have these 10,000 parsable papers, right? Like titles,
Right.
abstracts. Now you need to find, let's say you want k equal to 10, right? So now you need to find, first of all, 10 relevant papers, right? Among these 10,000. I mean, that's the first step that you will have to do, right?
Right.
So you're not yet using any kind of machine learning, nothing, right? You're just looking in these 10,000 for 10 relevant papers.
Right. With replacement, yes.
So what you're doing is you're just randomly taking one of these 10,000, looking at it. Is it relevant? Yes, no. If it is relevant, great, I have found one. If it's not relevant, I put it back.
Right.
Right. So now this process, depending on what k is, could mean you have to screen a lot of papers, right?
Right.
So, I mean, you don't have to screen 10,000, but you still, depending on how many relevant papers, actually relevant papers are among those 10,000, you still might be screening thousands of papers.
Right.
Right?
Exactly. Yeah.
So how much, I mean, I sort of see where you're going with this, right? So we might be cutting ultimately cutting down on some work, right? Because we have a certain guarantee to have a quite well-desired recall, let's say 90%, right? So we can, by making k sufficiently large, we have a high probability that we have at least 90% recall. Great. But to get k equal to sufficiently large so that probability is really high, I still will be screening thousands, possibly thousands of papers until I find at least k that are relevant. So how much ultimately will I save in terms of work?
Yeah, that's a great question. Yeah, I think kind of quite a big chunk of the workload to implement this algorithm is the first sampling process, because we really need to get so in order to get this kind of perfect protection, we have to have a perfectly randomly sampled papers, right? So that really takes time. And so in the paper, I did some simulated analysis on how those I did some simulated analysis on how the workload can be saved. So you could find more information there. But here, what I want to say is, so this the screening workload introduced by sampling can be reused. I mean, the information can be reused in the following screening process. I'm not sure if that makes sense.
Right, yeah, because you have seen that paper before, of course, and declared it to be relevant. So, I mean, okay, yeah, I see. Yeah, sure. I mean, you would have to do the screening anyway.
Right.
Yeah. And I have one other question. So now you have identified these k relevant papers, right? So now, of course, you're going to put them back into the pool, right? The machine algorithm for now, like that you're going to be using doesn't know, like it's going to rank, these 10,000. So well, look at this one first. Look at this one second. Is the algorithm allowed to change the order of which papers to look at after certain steps? Like, for example, if you update your algorithm after each step or after a batch of 100 or whatever, is the algorithm allowed to change the order?
Yes.
Okay.
Yes. The algorithm can do whatever the algorithm need to do, as long as they do not use the labeling information in the sampling process. So they can, so for example, this order may not be the order at the beginning, right? I'm just showing this order. It's like we have known the ground truth, and we know at the end of the day, if we're following the machine learning model, at the end of the day, the order is going to be like this. But at the beginning of this training process or like the screening process, the order may be, you know, quite different. But
Okay.
it doesn't matter. Yeah.
Okay, good. So this works whether the algorithm ends up reordering at certain points.
Right.
Okay, good.
Right.
Great. Thanks.
Yeah. Okay, yeah. So, another advantage of this algorithm is it will stop early if the model is a good, if the machine learning model is a good machine learning model, right? So it will stop here. I don't know which one would be a good. So, for example, right? So it will no. For example, it will stop at the 10th relevant paper anyway, but the total workload of the whole process really depends on how well the machine learning model can rank the 5,000 papers, right? If the machine learning model is able to kind of put all of the 100 relevant papers to the beginning of this process, which means it's quite a nice machine learning model, then the algorithm will stop quite early, right? But however, if some of those papers are ranked like very at a very are not predicted to be relevant even, right? So in that case, it's a bad prediction model, and this algorithm would stop quite late, right? It will allow us more time. It will require us to screen more because we are not using a good machine learning model, or like the machine learning model does not fit the papers, the data we have. So it's kind of adaptive process, right? If we have good model, we do not have to screen as much. If we have a bad model, we may have to, they would want us to screen more to make sure the performance is guaranteed. Yep. Right. Yeah, I have a question in the chat. Is there a reason I use recall as an indicator of accuracy? I think that's a great question because recall is basically, I think basically when we are doing this process, most of the scholars are cared or like concerned about the number of missing papers, right? So recall basically describes the proportion of missing papers. It's 1 minus the proportion of missing papers. So that's kind of the one thing that we are most interested in. And another thing is basically how much workload it's going to save. And the challenge of using recall to measure the performance of automatic literature screening is because this is not a deterministic process. It's a stochastic process. It basically means it starts from a random sample. It starts randomly. Even if it's just a machine learning model, we kind of randomly screen papers to be used as a training set, right? So if the training data is different, we have different results. So this is kind of a stochastic process, and we cannot use recall, which is one number, to describe it. So we may need to use the average recall, right? Like the expectation of recall. And if we use that, we probably also need to use the variance of recall, like how variable, how stable this algorithm is, and things like that. But I do think like recall is kind of more straightforward way to kind of measure the performance. We just need to consider the stochastic components here. Other indicate. So a following question is there any other indicators we would use I do not see any other things are used in the literature. Most of them are using recall. But yeah, like if you completely treat this as a machine learning algorithm, right? Like a classification problem, you could also use, like you could use accuracy, precision, and like false positive, false negative. Like there are so many metrics to if we treat this as a machine learning classification problem. There are so many well-developed metrics to measure the performance. But I personally do not think this is completely a classification problem. Thanks. Yeah, I think we are almost out of time. Before we stop, I just want to say I really appreciate your interest in this topic. I spent a lot of time working on this, and yeah, this is a great opportunity for me to present this work. And if you have any questions or if you want to discuss further, please just feel free to contact me. I'm always happy to have a conversation with you.
Thank you very much, Zhipeng. We've
Thanks.
got time for maybe one last question. I'll say last call.
Have you, I'll go, and this is kind of a tricky question, so maybe I don't know if you can answer it, but I wonder if you thought a little bit, any about using your like hit rate in your initial random sample to figure out how long it would take to get another new hit as you go, to try and estimate like how many
Right.
more attempts you should make before you cut it
Right.
off with respect to your sort of expected
Yeah.
increase in accuracy and the sort of total, there's like a lot of features there. Have you, is that in your
Right.
dissertation at all?
No, but that's a great idea. Yeah, it's a great idea. We definitely are able to estimate. This is called prevalence in machine learning world. Like prevalence is basically the proportion of relevant papers in this candidate pool. For example, in this example, we have 100 relevant papers and 5,000 candidate papers. The proportion is 100 divided by 5,000, which is 2%, right? This is the prevalence of this data set. But yeah, I do think it's a great idea to predict the total number or like the prevalence of this data set. But the challenge is most of the time the prevalence is too small. It's kind of, for example, this is in this scenario is only 2%, or like we probably have 5% or even 1%. So this is a very small number, small percentage to estimate, and it's kind of quite difficult for us to get an accurate estimation on the prevalence. This is kind of why it's challenging, but I think it's doable. Yeah, it's a great idea. I haven't done it yet, but it can be a great paper.
I'm not going to do it, so go for it.
Yeah. Great. Thank you once again. Thanks everyone for coming. We'll be back in April on, let's see, April 19th with Matt Granger from the Norwegian Institute for Nature Research, talking about the ES hackathon and sort of innovations in developing tools for evidence synthesis.
That's great.
Great. Thank you so much.
Thank you.
Can I
Really
ask you a
interesting.
question too?
Yeah.
I was just this is kind of a long, like Danny kind of stole my question, but I think maybe what he was getting at was like, if from the point of view of a user, it seems like it would be really helpful to have like a forecast of remaining workload. Right, like if
Right.
you're one of the screeners, you'd like to
Right.
know, oh my God, how much longer do I have to do all this?
Right.
That seemed like something that could be derived based on
Right.
based on the characteristics that you learned from the initial sampling?
Yeah, it's actually, we learned that very early. Like once the sampling is done and once
Yeah.
the model is trained, we already know, like maybe the model will change the order later, but once the prediction is done, we already know how many papers we need to screen,
Uh-huh.
right? Because we already know the stopping point. We just need to follow the process. But yeah, that's a great idea. I was even thinking about using that information to evaluate the performance of the model to tell if the model is good model or not.
Yeah.
But yeah, it's a great idea.
And have you thought at all about the like if someone wanted to have a guarantee on their recall or the stochastic guarantee, are there any implications for how they should modify their search? Right, because you can do searches with more or less specificity. So, you know, if you were using your algorithm, should that change your strategy for how you construct the initial search?
Yeah, that's a really interesting question. Because this algorithm works, it doesn't depend on the candidate pool size. The size of candidate pool does not. So I mean, this algorithm or like this formula really is quite general formula. So it doesn't limit anything. It doesn't limit model we use.
Yeah.
It doesn't limit total number of candidate papers and doesn't limit the proportion of relevant papers in the candidate pool. So I think people would want to be more general. Like we have more computing power nowadays. We have better machine learning and AI models
Right.
nowadays.
Yeah.
So it's definitely, we should be able to use more general kind of search prompts or like search keywords.
Yeah, but
Yeah,
that also increases the workload for the first stage, right?
Right. So
Right.
there's some interrelationship between like the prevalence in your pool and how long it's going to take for that random sample to turn up the
Right.
K that you're looking for, and then how many screening attempts that actually cuts out of the back end of your abstract screening process, which is a function of like how good the model is, which is sort of an unknown from the perspective of the screening process or that initial like random sample. But I wonder if there's some good literature on that you could use to sort of get an estimate of what your model was going to look like by the time that you're done, which is kind of a hard problem. But you know, it seems like there's a sort of there's a definite trade-off that's hard to know when you're doing that like more specific versus more general literature search.
Yeah.
Right. Yeah. That's great observation. I feel so happy that you think about that. It is a concern there.
It's a very elegant idea. I just say that, like, I thought, like, once I got where you were going with it, it really very cool. You know, so I think some of the most interesting, you know, solutions to problems are ones that are really simple but are sort of not in front of you until somebody points them out. So the approach is awesome. It's hard. It's sort of tricky, right, to know how much time it's going to save you. But as an idea, I love it. It's really interesting.
Thank you. Yeah, it's kind of mind-boggling, kind of. I feel it's kind of a good kind of homework question for statistics 101 students.
It demonstrates how like probabilistic thinking is not like natural, right? It's something it's very much trained. We're not good at doing that until we've had have our brains rewired in some way.
Right. Yep.